Tonight, we're going to cross a line that cannot be uncrossed. There is a specific point in space where gravity stops being a force you could ever fight against. Cross it, and every path through space-time that was once open to you collapses into a single direction, inward, and you are never coming back. And here's what makes this stranger than anything else in physics. That boundary isn't made of matter. You can't see it. You can't feel it when you pass through it. It doesn't glow. It doesn't emit radiation. It doesn't push back against you. It's just a location in empty space where the geometry of reality quietly but permanently changes. By the end of tonight, you're going to understand exactly what that boundary is, why it exists, what it does to space and time on either side, and why crossing it means something so profound that it challenges everything intuition tells you about the universe we live in. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. To understand why that boundary exists at all, you first need to understand what gravity actually is. And the answer isn't what most people learned in school. Most people were taught that gravity is a force, an invisible pull between objects with mass. The sun pulls on Earth. Earth pulls on the moon. Masses attract each other across empty space. That description works well enough for everyday engineering and navigation. It is accurate enough to calculate the trajectories of spacecraft, to plan interplanetary missions, to land a probe precisely on a moving target tens of millions of miles away. But it is not what is actually happening. In 1915, Albert Einstein published his general theory of relativity. What he showed, through a decade of extraordinarily difficult mathematical work, was that gravity is not a force at all. It is a curvature of space-time. Mass doesn't pull on other mass through empty space. What mass does is warp the geometry of the space and time around it. Objects then move through that warped geometry, following what are called geodesics, the straightest possible paths through a curved landscape. And what we interpret as gravitational attraction is just the result of objects following those paths through geometry that has been distorted. This is not a metaphor. It is not an analogy designed to make complicated physics easier to understand. It is the actual mathematical structure of how gravity works. The curvature is real, measurable, and has been confirmed by experiment after experiment. Starlight bends around the sun during solar eclipses, exactly as Einstein's equations predict. GPS satellites in orbit have to correct for the fact that time runs faster in weaker gravitational fields, meaning the satellite's clocks gain time relative to clocks on the ground. If those corrections weren't applied, GPS navigation would accumulate errors of several miles per day. The relativistic time correction is not a theoretical nicety. It is built into the actual software running in your phone. When you drop an object, it isn't being pulled toward Earth by some mysterious attractive force reaching across empty space. It is following a path through curved space-time. The curvature created by Earth's mass just happens to point toward Earth's center. The object moves along the straightest path available to it through geometry that tilts in that direction. The more mass you have, the more space-time curves around it. A bowling ball curves space-time a tiny amount. Earth curves it more. The sun curves it more still. And a black hole, where enormous mass has been compressed into an unimaginably small volume, curves space-time so severely that the geometry breaks down into something that has no equivalent anywhere else in the known universe. The concept of an object so massive that nothing could escape it is older than Einstein. In 1783, a British clergyman and amateur natural philosopher named John Michell was working through the implications of Newtonian gravity and the emerging understanding of light. He knew that a cannonball fired upward from Earth would slow down, stop, and fall back. The faster you fired it, the higher it would travel before turning around. Fire it fast enough, and it would escape entirely. That minimum speed, the speed above which an object can escape a body's gravity and never return, is called escape velocity. For Earth, the escape velocity is about 25,000 miles per hour. For the Sun, it is about 1,370,000 miles per hour. Michel asked a deceptively simple question. What if you had a body so massive and dense that its escape velocity equaled or exceeded the speed of light? Using the physics available to him, he reasoned that light would be unable to escape from such an object. It would be perpetually trapped. The object would be dark, invisible. He called them dark stars, and he published this idea in a paper for the Royal Society. The idea attracted little attention. It wasn't taken seriously by the broader scientific community, partly because light wasn't well understood at the time, and partly because the mathematics to explore it properly didn't yet exist. The idea faded. Then came Einstein. In 1915, he published the field equations of general relativity, and in 1916, just months after the publication, while serving on the Russian front during the First World War, a German physicist and astronomer named Karl Schwarzschild found an exact solution to those equations. He was working through the mathematics in whatever quiet moments he could find between the fighting. He sent the solution to Einstein in a letter, and Einstein was reportedly astonished by how quickly it had been found and by its elegance. Schwarzschild's solution described the geometry of space-time around a perfectly spherical, non-rotating, electrically neutral mass. It was a clean, exact result. But embedded in that solution was something unexpected. There was a critical radius, a specific distance from the center of any mass at which the mathematics produced a singularity. The geometry didn't just curve severely there. The equations produced infinite values. The metric, which is the mathematical object that encodes the geometry of space-time, broke down completely at that radius. Schwarzschild himself believed this was a mathematical artifact with no physical meaning. He thought that nothing in nature could actually be compressed small enough for that radius to fall outside the object itself. He was wrong. That critical distance is now called the Schwarzschild radius, and it exists for every object in the universe. Every single one, regardless of how ordinary it is. For Earth, the Schwarzschild radius is approximately 1/3 of an inch. That is the size to which you would have to compress the entire mass of Earth to create a black hole. All of it, squeezed into a sphere smaller than a marble. For the Sun, the Schwarzschild radius is about 1.9 miles. Squeeze all the Sun's mass into a sphere just under 4 miles in diameter, and you would cross the threshold. Under ordinary circumstances, none of this matters. Earth is not going to collapse into a black hole. The Sun is not going to collapse into a black hole. The Schwarzschild radius of these objects sits deep inside them, in a region where the matter of the object itself provides the pressure to resist further collapse. But when massive stars run out of nuclear fuel and their cores collapse under gravity, something different happens. The collapse is sudden and violent. In less than a second, the core of a dying star can go from something the size of Earth to something the size of a city. If the core is massive enough, roughly more than about 3 times the mass of the Sun after the collapse, then nothing stops it. Electron degeneracy pressure, the quantum mechanical resistance of electrons to being crowded together, is overwhelmed. Neutron degeneracy pressure, the same resistance applied to neutrons, is overwhelmed. Every known form of pressure fails. The collapse continues all the way down to a point of essentially zero volume and infinite density, which in mathematics is called a singularity. At that point, all the mass of the core sits inside a sphere far smaller than the Schwarzschild radius. A black hole exists, and surrounding it, at the exact Schwarzschild radius, is the event horizon, the invisible surface that defines the point of no return. The point in space where gravity becomes irreversible. The word horizon is chosen deliberately. A horizon in everyday life is a boundary beyond which you cannot see. Stand on a flat plane and look toward the edge of the world. You can see everything out to the horizon. Beyond it, the curvature of the planet hides things from your view. Events happening beyond the horizon are invisible to you, not because they're extraordinary, but simply because the geometry of the situation puts them out of reach. The event horizon of a black hole is similar in name only. The physical reality is far more fundamental. The event horizon is not a boundary beyond which you cannot see. It is a boundary beyond which events are causally disconnected from the rest of the universe. Not just invisible, causally disconnected. What that means requires a moment to properly absorb. In physics, 2 events are causally connected if one could have influenced the other. You can influence a future event if you can send a signal to it, a light beam, a radio wave, a gravitational disturbance, anything traveling at or below the speed of light. If you cannot send any signal between 2 events, they are causally disconnected. They cannot influence each other. Inside the event horizon, no signal of any kind can travel outward. Not light. Not radio waves. Not gravitational influences. Not any form of information or energy. The reason is not that the signal encounters some barrier and gets blocked. The reason is geometrical. Inside the horizon, the structure of space-time is arranged so that all paths going outward are actually going inward. Space-time has been curved so severely that what you might call the outward direction simply doesn't exist anymore. There are no outward paths. Every path leads inward. The geometry of space-time has been rearranged so that inward is the only direction time flows. To understand what this really means, you need to know how physicists think about the structure of space-time around paths. In normal flat space-time, imagine yourself at a particular location at a particular moment. Every possible direction you could move, every possible path you could travel into the future, is contained within what's called your future light cone. Think of it literally as a cone opening upward from your current position. Light travels outward in all directions from your location, forming the surface of the cone. Any path you can travel must be inside that cone, because you can't move faster than light. Your future is everything inside and on the surface of that cone. As you approach a black hole, the intense curvature of space-time begins to tilt that cone. The cone itself, which represents all possible futures, starts rotating inward toward the black hole. More and more of the cone's interior is pointing toward the black hole's center. At the event horizon, the tipping is complete. The cone has been tilted so far inward that every possible future path, including the path light would take, trying to move directly away from the black hole, is pointing toward the singularity. The entire future light cone is aimed inward. There are no paths available that lead outward. Light, trying to escape from exactly at the event horizon, simply hangs there, suspended at the boundary, making no progress outward. Light slightly inside the horizon is moving inward, even if it's aimed in what locally seems like the outward direction. And for any massive object that has crossed the horizon, the situation is analogous to what we experience with time. You cannot stop time. You cannot reverse it. You cannot opt out of moving forward in time. You might move fast or slow through space. You might choose different locations, but the arrow of time carries you forward regardless of your preferences. Inside a black hole, the inward direction toward the singularity has the same character as the forward direction of time everywhere else. You will move toward the singularity, not because a force is pushing you, because inward is what future means inside the event horizon. The size of an event horizon depends entirely on the mass of the black hole. The relationship is direct and linear. Double the mass, double the Schwarzschild radius. A black hole, 10 times the mass of the Sun, has an event horizon about 18 miles across from one side to the other. A black hole, 100 times the mass of the Sun, has one about 180 miles across. A supermassive black hole with 1 million solar masses has an event horizon spanning about 3.7 million miles, roughly 4 times the distance from Earth to the Moon. A supermassive black hole with 1 billion solar masses has an event horizon spanning about 3.7 billion miles, which is roughly the size of Neptune's orbit around the Sun. These numbers scale upward cleanly. The most massive black holes discovered so far, the so-called ultramassive black holes at the centers of the largest and most ancient galaxies, contain tens of billions of solar masses. The black hole at the center of the galaxy TON 618, a quasar over 10 billion light-years away, has a mass of about 66 billion solar masses. Its event horizon has a radius of roughly 120 billion miles. An event horizon wider than the distance across our entire solar system, many times over. And yet, the event horizon of TON 618 is just a surface, an invisible geometric boundary in space. Not a physical structure, not a wall, not matter of any kind. Just a place in space where the geometry has changed. This is the detail that surprises people most when they first encounter black hole physics. The event horizon is not a dramatic place locally. For a large enough black hole, you would not feel anything special as you crossed it. No dramatic force, no alarm, no visible boundary. The space-time curvature at the horizon of a supermassive black hole is actually quite gentle by local standards. The change in gravity across the length of your body, what physicists call the tidal force, can be small enough that your body would feel nothing extraordinary. You could cross the event horizon of a sufficiently massive black hole and have absolutely no physical sensation that distinguishes that moment from any other moment during your infall. This is deeply counterintuitive. People imagine the event horizon as a dramatic threshold, a place where extreme forces announce themselves, where something physical prevents you from leaving. But there is no such announcement. There is no wall. There is no force at the boundary. The event horizon is not a thing you can touch or detect locally. It is a global property of the space-time geometry, a consequence of how the curvature is arranged on large scales. You have crossed the most absolute boundary in physics, and nothing in your immediate environment told you it happened. All the exits are gone. The universe outside continues exactly as it was, without any indication that something irreversible has just occurred. For a smaller black hole, the situation at the horizon is different. A stellar mass black hole of 10 or 20 solar masses has a much smaller event horizon, and the tidal forces there are extreme. The difference in gravitational pull between your head and your feet, across the roughly 6 feet of your body, would be catastrophically large. This differential tearing force, which physicists sometimes call spaghettification, would stretch your body vertically and compress it horizontally, pulling you apart into a long, thin strand of matter and energy. For a small enough black hole, this process begins well before you reach the event horizon itself. The tidal forces would be lethal, far outside the boundary. But this is a feature of the size, not the horizon itself. For the supermassive varieties, the horizon is quiet. The violence comes later, as you approach the singularity deep inside. Now we need to understand what the event horizon does to time. Time is not what most people think it is. It is not a fixed, universal, absolute quantity that flows at the same rate everywhere. This is one of the things Einstein's relativity made unmistakably clear. Time is relative. It passes at different rates depending on where you are and how you're moving. Specifically, time runs slower in stronger gravitational fields. This is called gravitational time dilation, and it has been measured and verified in experiments that leave no room for doubt. The GPS satellites orbiting Earth are in a region of weaker gravity than the ground. Their clocks run faster than clocks on Earth's surface. The difference is about 45 microseconds per day from gravitational time dilation. There's also a competing effect from their velocity, which makes their clocks run slower by about 7 microseconds per day. The net result is that GPS satellite clocks gain about 38 microseconds per day relative to ground clocks. This is not a small effect in the context of precision navigation. Accumulated over a day, without correction, this error would cause positional errors of several miles. The correction is applied continuously and automatically. It works because Einstein's relativity is correct. This is the first thing to hold on to. Now apply gravitational time dilation near a black hole. As you fall toward the event horizon, time dilation becomes increasingly severe. Your clock, from the perspective of a distant observer watching you, runs slower and slower. An observer far away from the black hole, watching you fall with a very powerful telescope, would see your movements gradually slow. Your light becomes increasingly redshifted as it has to climb out of the deepening gravitational well to reach them. The redshift becomes more and more extreme as you approach the horizon. At the horizon itself, the time dilation becomes infinite. From the distant observer's perspective, your clock would appear to stop entirely. You would appear to freeze. Your image would dim and redden as your light becomes stretched to longer and longer wavelengths, eventually fading from visible to infrared to radio, until you effectively vanish from detectability. You appear to the outside universe to hover at the event horizon forever, frozen in time. You never appear to cross. From the outside universe's perspective, nothing ever actually falls through an event horizon. Everything appears to freeze at the boundary, gradually fading from view. But from your own perspective, Inside your own reference frame, none of this is happening. You fall through the horizon in a finite and sometimes quite short amount of your own time. Your clock ticks normally. You feel no extraordinary slowing. You experience no freezing. You cross. And this is where general relativity requires you to set aside the intuition that there must be one true account of what happened. Both descriptions are real. Both are accurate. The frozen at the boundary account is what the distant observer genuinely measures using real clocks and real instruments. The falls through normally account is what the infalling observer genuinely experiences using their own real clocks. General relativity tells us that there is no single universal description that all observers agree on. Different reference frames can disagree profoundly about sequences of events, about simultaneity, about what happens when. The event horizon makes this maximally vivid. Two observers start with a shared history, then one crosses the horizon, and from that point forward, their descriptions of reality diverge completely and can never be reconciled. Because no signal can carry information from one to the other. In 1963, a New Zealand mathematician named Roy Kerr found a new solution to Einstein's field equations. Schwarzschild's solution described a non-rotating black hole. Kerr's solution described something more realistic, a rotating one. In nature, virtually everything rotates. Stars rotate. Planets rotate. Galaxies rotate. When a massive star collapses, the rotating core doesn't stop rotating. Conservation of angular momentum means the rotation speeds up dramatically as the core shrinks, the same way a spinning figure skater spins faster when they pull their arms in. A collapsing stellar core goes from perhaps one rotation per month to potentially hundreds of rotations per second. The result is a black hole that is spinning, sometimes at a significant fraction of the maximum rate that physics allows. The Kerr solution, which describes the geometry of spacetime around such a rotating mass, is considerably more complex than Schwarzschild's. A rotating black hole has not one event horizon, but two. The outer event horizon is the point of no return in the sense we've been discussing. Cross it, and you cannot return to the outside universe. The inner horizon is a second boundary, deeper inside, where the nature of space-time changes, again in ways that our current understanding does not fully resolve. The physics near the inner horizon is connected to some of the deepest unresolved questions in theoretical physics, relating to stability and what an infalling observer would actually experience. But there's another feature of the Kerr solution that has no counterpart in the Schwarzschild case. It is called the ergosphere. The ergosphere surrounds the outer event horizon like a flattened bubble, extending outward from the poles and bulging at the equator. It sits outside the event horizon and is therefore not a region of no return. Things can enter the ergosphere and leave. But inside the ergosphere, space-time itself is dragged around by the black hole's rotation. This effect is called frame dragging, and it exists outside the ergosphere too. Any rotating mass drags space-time around with it, pulling local inertial frames into rotation. Earth does this, but so weakly it is barely measurable. A rapidly rotating black hole does it so dramatically that inside the ergosphere it is impossible to remain stationary. Even if you fired your rocket engines with maximum thrust in the direction opposite the black hole's rotation, trying to hold your position, you would still be dragged around. Space-time itself is moving, carrying you with it. Everything inside the ergosphere must orbit the black hole. Not because a force is pushing it, because the geometry says orbital motion is the only option. The ergosphere has a consequence that at first sounds like it shouldn't be possible. Because it is outside the event horizon, it can in principle be used to extract energy from the rotating black hole. This is called the Penrose process, described by physicist Roger Penrose in 1969. The basic idea is that you send an object into the ergosphere and have it split into two pieces in precisely the right way. One piece falls inward, past the event horizon. The other piece escapes outward. If the geometry and the splitting are arranged correctly, the escaping piece can emerge, carrying more energy than the original combined object brought in. The extra energy comes from the black hole's rotational energy. The black hole slows down slightly. Energy has been extracted. The Penrose process doesn't happen spontaneously in nature in any simple way, but it is consistent with all the known laws of physics. It means that rotating black holes are not purely passive sinks that absorb everything and return nothing. They are objects with rotational energy that can, in principle, be tapped. Astrophysicists believe that some variation of this process, involving magnetic fields and the accretion of matter, is responsible for the enormous jets of particles that many active black holes produce. Jets that can extend for millions of light years and rival entire galaxies in luminosity. The event horizon and the ergosphere working together, in other words, can be the engine driving some of the most energetic phenomena in the observable universe. The first direct image of a black hole was released on April 10, 2019. The Event Horizon Telescope collaboration, a network of radio observatories spread across the entire planet and functioning together as a single Earth-sized telescope, produced an image of the region around the supermassive black hole at the center of Messier 87. Messier 87 is a giant elliptical galaxy about 54 million light-years away in the constellation Virgo. Its central black hole contains about 6.5 billion solar masses. Getting to that number required years of careful work using multiple observation techniques. Tracking the motions of stars and gas orbiting the black hole. Measuring the brightness and shape of the accretion disk. Cross-checking with independent methods. The event horizon radius implied by that mass is about 12 billion miles, larger than the orbit of Saturn in our solar system. An enormous volume by human intuition. But remember, the Milky Way alone spans 100,000 light-years. Even the event horizon of this extraordinary object is a point by galactic standards. What the image shows is not the event horizon directly. You cannot photograph something from which no light escapes. What it shows is the shadow the black hole's event horizon casts against the glowing ring of hot gas orbiting around it. That gas, the accretion disk, is falling inward toward the black hole. It has been compressed and heated by the intense gravity to temperatures of billions of degrees. It radiates brilliantly in radio frequencies. And in the center of that glowing ring, there is darkness. Not the darkness of empty space. The darkness of an absence of light produced by a geometry that redirects all light inward. The shadow. The image showed an asymmetric ring, brighter on one side than the other. This asymmetry is a real physical effect. The gas on the side of the disk, orbiting toward us, is blue-shifted, its radiation boosted in brightness by its motion. The gas, orbiting away from us, is red-shifted and dimmed. The result is a lopsided ring. And that lopsidedness, that specific pattern of brightness, was exactly what Einstein's equations predicted it would look like. The image was a verification of general relativity in an extreme regime that had never before been directly observed. Producing that image required coordinating observations across telescopes in Antarctica, Chile, Hawaii, Spain, Mexico, and Arizona. The observations had to happen simultaneously during a narrow window when weather conditions at all sites were favorable. The data from each site was recorded on specialized hard drives and physically shipped to processing centers because the volume of data made network transfer impractical. Petabytes of information had to be synchronized and analyzed before the image could be assembled. The entire project was a technical achievement of the first order. 3 years later, in 2022, the same collaboration released an image of the second black hole they had targeted, Sagittarius A, at the center of our own Milky Way. Sagittarius A sits 26,000 light-years from Earth. It contains about 4 million solar masses. Its event horizon has a radius of about 7.4 million miles. Getting that image was significantly harder than Messier 87's. Because Sagittarius A is much smaller, gas orbiting near its event horizon completes an orbit in minutes rather than the days it takes for gas near Messier 87. The image was shimmering and changing on short timescales. The team had to develop new techniques to handle this variability, averaging and reconstructing thousands of snapshots to produce a stable final image. But they got it. The same structure, a bright ring surrounding a dark shadow, 2 event horizons photographed, 2 points of no return made visible in their way for the first time. In 1974, Stephen Hawking published a result that changed the way physicists think about black holes. Before his paper, black holes were understood as purely absorbing objects. Mass, energy, and information could fall in. Nothing could come out. They were cold, dark, silent. Objects defined entirely by what they consumed. Hawking showed that this picture is incomplete. Quantum mechanics changes it. Empty space, in quantum mechanics, is not truly empty. The vacuum is filled with constant quantum fluctuations. Pairs of particles and their antiparticles continuously appear from the vacuum, exist for a fleeting moment, and then annihilate each other, returning their borrowed energy to the vacuum. This is called virtual particle production, and it happens everywhere in space, all the time. Normally, the pairs annihilate almost immediately and leave no lasting effect. But near the event horizon of a black hole, something different happens. A particle pair appears right at the horizon. One member of the pair finds itself just inside the horizon. The other finds itself just outside. They can no longer meet to annihilate because the horizon separates them. The inside particle falls inward toward the singularity. The outside particle escapes outward into space. From the perspective of an observer far from the black hole, it looks as though the black hole is spontaneously emitting a particle. Energy has been radiated away. This is Hawking radiation. The temperature of this radiation depends on the black hole's mass. Specifically, the Hawking temperature is inversely proportional to the mass. For a stellar mass black hole of 10 solar masses, the Hawking temperature is about 6 billionths of a degree above absolute zero. This is far colder than the cosmic microwave background radiation that fills all of space, which has a temperature of about 2.7 kelvins. Hawking radiation from stellar mass black holes is undetectable against that background. It's not that we lack sensitive enough instruments. It's that the signal is genuinely swamped by the ambient temperature of the universe itself. For a supermassive black hole of 1 billion solar masses, the Hawking temperature is even lower. Essentially, unmeasurably close to absolute zero. But for smaller black holes, the temperature rises. A black hole with the mass of a mountain would radiate at visible temperatures. A black hole with the mass of a large asteroid would be hot enough to be intensely luminous. And a microscopic black hole, if such a thing could exist, would be so hot that it would radiate explosively, shrinking rapidly and ending in a burst of high-energy radiation. The key implication of Hawking radiation is that black holes slowly lose mass. They emit energy, and because mass and energy are equivalent through the relationship E equals mc squared, this means they're converting their mass into radiation. For large black holes, this process is extraordinarily slow. A black hole with 10 solar masses would take something like 2 × 10⁻⁶ years to evaporate completely through Hawking radiation. For comparison, the current age of the universe is about 13.8 billion years. The number 2 × 10⁻⁶ is incomparably larger. But the process is real. It happens. And as a black hole loses mass and shrinks, the Hawking temperature rises. A shrinking black hole radiates faster, shrinks faster, raises its temperature further, radiates even faster. In the final moments of a black hole's life, the process accelerates into an explosive final burst. The event horizon shrinks to nothing. And then it's gone. What happened to everything that fell in? This question is not trivial. It is one of the central unresolved problems in theoretical physics, and it has been for over 50 years. When matter falls into a black hole, it carries information. The information about what it was made of, how its atoms were arranged, what quantum state it was in. Every physical system carries information of this kind. Quantum mechanics says, in very precise mathematical terms, that information cannot be destroyed. This is not a principle physicists chose to adopt because it seemed philosophically satisfying. It is a consequence of the mathematical structure of quantum mechanics. The equations that describe how quantum systems evolve over time have a specific property called unitarity, which ensures that information is always conserved. You can scramble information. You can distribute it across many particles. You can make it extremely difficult to recover. But you cannot destroy it. General relativity, on the other hand, produces a picture in which black holes that evaporate via Hawking radiation appear to destroy information. All black holes of the same mass, angular momentum, and electric charge produce identical Hawking radiation. The radiation contains no information about what fell in. Throw in a star. Throw in a library. Throw in a handful of elementary particles. You get the same featureless thermal radiation back. When the black hole finishes evaporating, that information appears to be gone. No encoding of it survives in the outgoing radiation. This is the black hole information paradox. It is a conflict between two theories that are each individually extraordinarily successful. General relativity has passed every experimental test applied to it. Quantum mechanics has passed every experimental test applied to it. But they appear to give contradictory answers to what happens to information inside a black hole. Hawking himself initially believed that information was genuinely lost. That black holes represented a real exception to quantum mechanical unitarity. That the universe would simply have to live with this. He later changed his view, accepting that information probably escapes somehow, but the question of how remained open. The problem is that any mechanism for information escape has to contend with the fact that nothing can travel outward through the event horizon. If information escapes in the Hawking radiation, it cannot do so by simply climbing through the horizon. The horizon is the definition of the barrier to such escape. Some mechanism must exist that encodes the information in the outgoing Hawking radiation without violating the geometry of the event horizon. Working out that mechanism in a mathematically precise and consistent way has been the project of a significant fraction of theoretical physics for decades. In recent years, progress has been made using a framework called the island formula. This approach, drawing on deep connections between quantum mechanics and the geometry of spacetime, suggests that information is indeed encoded in the Hawking radiation, but through a subtle and non-local mechanism that doesn't require information to climb through the horizon in any simple sense. The full picture is still being worked out. The mathematics is intricate. The physical interpretation is debated. But the weight of current theoretical evidence seems to be moving toward the view that information escapes. The event horizon, which appears to destroy information from the outside, somehow does not actually destroy it. The mechanism by which this happens remains one of the deepest open questions in physics. There is a related crisis that emerged from a careful analysis of what information escape would require. In 2012, 4 physicists, Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully, published a paper that became known by the initials of their names, AMPS. They worked through the logical consequences of requiring that information escape from black holes in Hawking radiation. And they found that those consequences were alarming. Quantum mechanics requires that the Hawking radiation emitted at different times must be quantum mechanically entangled with each other in the right way to carry information outward. But there's a rule in quantum mechanics called the monogamy of entanglement, which says that a particle can only be maximally entangled with one other thing. If the early Hawking radiation is entangled with the late Hawking radiation in the way needed for information to escape, then it cannot also be entangled with the matter that fell into the black hole. But if it's not entangled with the matter that fell in, then the quantum state of the matter inside the black hole is completely disconnected from the quantum state of the radiation outside. And the mathematical structure of quantum field theory, which describes how particles behave near the event horizon, seems to require that such a disconnection would be accompanied by a burst of extremely high-energy radiation right at the horizon, a firewall. Rather than crossing the horizon smoothly and unremarkably, as general relativity predicts, an infalling observer would encounter an effectively solid wall of intense radiation. The event horizon in this picture would not be a quiet boundary. It would be a place of violent destruction. The AMPS firewall paradox put 3 foundational principles of physics into apparent conflict. General relativity says the event horizon is locally unremarkable. Quantum mechanics says information must be conserved. The equivalence principle, one of the cornerstones of general relativity, says that a freely falling observer should not be able to distinguish free fall from floating in empty space. A firewall violates the equivalence principle. All 3 of these principles cannot simultaneously be true if the firewall analysis is correct. at least one of them has to be modified or abandoned. Physicists disagree on which one. Some accept the firewall and look for ways to modify our understanding of the event horizon. Others believe the firewall resolution will require new physics that doesn't yet exist. Others argue that the paradox reveals that the interior of a black hole is not an independent region of space-time, but is somehow encoded on or equivalent to the exterior, an idea related to the holographic principle. What is not in dispute is that the event horizon sits precisely at the fault line between our two most successful theories of physics. The point in space where gravity becomes irreversible is also the point where our current understanding of the universe strains to its limits. The holographic principle is an idea that grew directly from thinking carefully about what the event horizon means. In the early 1970s, when Stephen Hawking was working out the thermodynamics of black holes, he found a remarkable relationship. Working with a physicist named Jacob Bekenstein, he established that black holes have entropy. Entropy is a measure of the information content of a physical system. For ordinary objects, entropy is proportional to the number of ways the object's constituents could be arranged while still producing the same macroscopic appearance. More particles, more possible arrangements, more entropy. And entropy, for ordinary objects, scales with volume. A box twice as big has twice the volume and can hold twice as many gas molecules, and so has roughly twice the entropy. But for a black hole, Hawking and Bekenstein found that the entropy is proportional not to the volume of the black hole, but to the area of its event horizon. The Bekenstein-Hawking entropy formula states that the entropy equals the area of the event horizon divided by 4 times the square of the Planck length. The Planck length is about 1.6 times 10 to the negative 35 meters. It is the smallest length scale at which our current theories of physics are expected to be reliable. At that scale, quantum effects of gravity become significant, and our understanding breaks down. The Bekenstein-Hawking formula says that each unit of Planck area on the event horizon corresponds to 1 bit of information about the black hole's interior. All the information that describes everything inside the black hole, all the matter and energy and quantum states that have ever fallen in, is encoded on the surface of the event horizon, not in the volume. On the surface. This is the first hint of the holographic principle. It suggests that the 3-dimensional interior of a black hole is, in some deep sense, described completely by the 2-dimensional surface surrounding it. A physicist named Gerard 't Hooft and independently Leonard Susskind generalized this into a broader conjecture. Perhaps this is a general feature of physics. Perhaps all the information in any volume of space is encoded on a surface surrounding that volume. The universe might be fundamentally holographic in nature. The most mathematically precise realization of this idea came from Juan Maldacena in 1997. Maldacena discovered a precise mathematical equivalence, called a duality, between a theory of gravity in a particular type of curved spacetime and a quantum field theory without gravity living on the boundary of that spacetime. The two theories, one with gravity in the bulk and one without gravity on the boundary, describe exactly the same physical reality. Every calculation in one corresponds to an equivalent calculation in the other. This is called the anti-de Sitter, conformal field theory correspondence, or ADS, CFT for short. It is one of the most influential theoretical results in physics of the past 3 decades. It has been used to study strongly coupled quantum systems, plasma physics, condensed matter systems, and the behavior of black holes. And it started from the event horizon. From asking what it means that a black hole encodes all its information on a surface. From the strange fact that the boundary counts as much as the interior. The event horizon is not just a geometric feature of a massive object. It may be a window into the deepest structure of reality, into a universe where surfaces and volumes, where 2 dimensions and 3 dimensions are not as distinct as they seem. In addition to stellar mass and supermassive black holes, physicists have proposed a third category: primordial black holes. These would be black holes formed not from collapsing stars, but from the extreme density fluctuations in the very early universe. In the first fractions of a second after the Big Bang, the universe was a hot, dense plasma, compressed to extraordinary densities. Small regions, slightly denser than average, could have collapsed directly into black holes under their own gravity, without the intermediate step of forming stars first. The mass of a primordial black hole would depend on the specific conditions when it formed, and could range from the mass of a large asteroid to many solar masses or more. Primordial black holes, with masses smaller than about 10 to the 12 kilograms, would have evaporated via Hawking radiation by now. The Hawking temperature for such small objects is high enough, and the evaporation rate fast enough, that they would not survive to the present day. But more massive primordial black holes could still exist, and they have attracted attention as a possible component of dark matter. Dark matter is the name for whatever provides the extra gravitational force that holds galaxies and galaxy clusters together beyond what ordinary visible matter can explain. It comprises about 85% of all the matter in the universe. It does not emit, absorb, or reflect light. We infer it entirely from its gravitational effects. If even a fraction of this dark matter consists of primordial black holes, there would be event horizons scattered throughout the cosmos. Ancient boundaries between the accessible universe and irreversible gravity, present since nearly the beginning of time. Searches for primordial black holes are ongoing. One approach is gravitational microlensing. When a compact, massive object, including a black hole, passes in front of a distant star, it acts as a gravitational lens, bending the star's light and causing it to temporarily appear brighter. The pattern and duration of this brightening depends on the mass of the lensing object. Surveys of millions of stars looking for this characteristic brightening have constrained how many primordial black holes can exist in certain mass ranges. So far, the results have ruled out some mass ranges as the dominant component of dark matter, but left others open. The search continues. There are objects that sit just outside the boundary of becoming a black hole, and they are extraordinary in their own right. Neutron stars. When a stellar core collapses and the remaining mass is between roughly 1 and 3 solar masses, the collapse halts at a different threshold. Rather than continuing all the way to a singularity, the collapse is stopped by neutron degeneracy pressure. Neutrons, like electrons, resist being packed too closely together due to the Pauli exclusion principle, a quantum mechanical rule that prevents identical fermions from occupying the same quantum state. The resulting object is a neutron star. Neutron stars are remarkable by any measure. They typically contain about 1 to 2 solar masses compressed into a sphere roughly 12 to 15 miles in diameter. This density is so extreme that a single teaspoon of neutron star material weighs approximately 10 billion tons. Gravity at the surface of a neutron star is about 200 billion times stronger than gravity at Earth's surface. Neutron stars rotate. They rotate very fast. As the stellar core collapses, conservation of angular momentum spins them up from their original leisurely rotation to rates of up to hundreds of revolutions per second. Some neutron stars emit beams of electromagnetic radiation from their magnetic poles, and as they rotate, those beams sweep across space like cosmic lighthouses. When such a beam happens to sweep past Earth with each rotation, we detect it as a regular pulse. These are called pulsars. Pulsars are among the most precise natural clocks in the universe. The timing of their pulses is so regular that any deviation can be measured with extraordinary precision, allowing them to be used as tools for testing general relativity and even for detecting gravitational waves. The key distinction between a neutron star and a black hole is that a neutron star has no event horizon. It has a surface. Things that fall onto a neutron star hit the surface. Light can escape from a neutron star. There is no point of no return, at least not in the same sense. But neutron stars exist right at the edge. If you added enough mass to a neutron star to push it above the maximum mass that neutron degeneracy pressure can support, typically thought to be somewhere between 2 and 3 solar masses, 214, the collapse would resume. Neutron degeneracy pressure would be overcome. The collapse would proceed all the way to a singularity. An event horizon would form. The neutron star would become a black hole. This transition can happen through mass accretion, where a neutron star in a binary system slowly pulls matter from its companion until it becomes too massive. Or it can happen through a violent collision when two neutron stars in a binary spiral together and merge. In August 2017, the LIGO and Virgo gravitational wave detectors simultaneously detected the gravitational waves from two merging neutron stars. The event happened about 130 million light-years away. The gravitational wave signal arrived at Earth after traveling that distance. Within seconds, telescopes across the planet were pointed at the source. An extraordinary explosion was seen, a kilonova, the spectacular electromagnetic fireworks produced when two neutron stars collide and merge. The kilonova produced enormous amounts of heavy elements: gold, platinum, uranium, all the elements heavier than iron that cannot be produced in ordinary stellar burning. They were forged in the nuclear physics of the collision. And then, at the end of that violence, the merger product collapsed. It exceeded the maximum mass that neutron degeneracy pressure could support. An event horizon blinked into existence 130 million light-years away. The birth of a new black hole, marked simultaneously by the most dramatic electromagnetic display and the first multi-messenger gravitational wave event ever detected. The gold in your jewelry, the platinum in the catalytic converter of a car, the uranium in nuclear reactors, all of these began their existence in events like that one, forged in the moment, surrounding the formation of an event horizon. The point of no return was the punctuation mark at the end of a sentence written in the most energetic physics the universe produces. The event horizon also has a face that looks outward. From the perspective of someone watching the black hole, not falling into it. An outside observer with a telescope, pointing it at a black hole, sees things that general relativity predicted and that observations have confirmed. The light from objects near a black hole is gravitationally lensed. The warped space-time bends the paths of light beams, magnifying distant objects, creating multiple images of the same source, and producing arcs and rings of light. This is the same effect that makes galaxy clusters act as gravitational lenses for more distant galaxies behind them, something seen in many famous Hubble Space Telescope images. But near a black hole, the effect is far more extreme. Light bending at such dramatic angles creates structures that don't exist anywhere else. The photon sphere is the most striking example. This is a region outside the event horizon, where gravity is strong enough for light to travel in circular orbits. For a non-rotating black hole, the photon sphere sits at 1.5 times the Schwarzschild radius, 1.5 times as far from the singularity as the event horizon itself. At the photon sphere, a photon can orbit the black hole indefinitely, going around and around in a circle. These orbits are unstable. A photon exactly at the right distance can orbit, but the slightest perturbation either sends it spiraling inward to be captured or sends it spiraling outward to escape. The photon sphere is the gravitational equivalent of a mountain peak that is perfectly flat at the top. You can balance there, but any tiny nudge rolls you off in one direction or the other. There is no stable resting position. The photon sphere is responsible for one of the most striking aspects of black hole images. When the Event Horizon Telescope looked at Messier 87, it was seeing photons that had originated in the accretion disk and been bent by gravity into the configuration of the image. Light from the disk behind the black hole was bent around it and arrived at telescopes on the opposite side. Light from the top of the disk was bent downward. Light from the bottom was bent upward. Light from the sides curved around to fill in the ring. The bright ring in the image is light from the photon sphere region and the accretion disk bent by gravity into a luminous ring as seen from Earth. The dark region in the center, the shadow, is actually larger than the event horizon itself. It is roughly 2.5 times the event horizon radius. The shadow is created by the fact that any photon aimed at the event horizon or aimed close enough to it to spiral inward never reaches an outside observer. The shadow represents all the angles from which no photons reach us. The event horizon is inside that shadow, hidden within a darkness that is itself created by the geometry of space-time around the horizon. The event horizon is invisible within the invisible. There is a category of objects so extreme that they challenge the distinction between a black hole and a supermassive core. Ultramassive black holes at the centers of the largest ancient galaxies have masses in the tens of billions of solar masses. The galaxy Home 15A times hosts a black hole of roughly 40 billion solar masses. Its event horizon has a radius of about 123 billion miles. That single geometric boundary, the invisible surface marking the point of no return, encloses a volume wider than our entire solar system many times over. Nothing physically dramatic marks that boundary from the inside. Gravity there, at the horizon of a 40 billion solar mass black hole, is extraordinarily mild by comparison to its mass. The tidal forces at the horizon are so gentle that a human body would barely notice them. You could be falling through the event horizon of that black hole several billion years after its formation and feel nothing more dramatic than floating in empty space. There would be no announcement, no signal. Nothing that told you the most consequential crossing in the universe had just occurred. The contrast between the enormity of what that boundary means, the permanent severance from the entire rest of the universe, and the complete physical gentleness of the moment of crossing is one of the most philosophically striking facts in all of physics. Significance and sensation have been completely decoupled. The most absolute boundary has zero local physical signature. We need to talk about what happens as you continue falling after crossing the horizon, specifically as you approach the singularity. For a non-rotating Schwarzschild black hole, the mathematics of general relativity says that after crossing the horizon, the singularity is not in a place. It is in the future, in a genuinely literal sense. Outside the horizon, the singularity is in a spatial direction, toward the center. You can avoid it by not going that way. But inside the horizon, the structure of space-time is such that the singularity is ahead in time, not ahead in space. It is where time goes. You cannot avoid the singularity any more than you can avoid tomorrow. The time between crossing the horizon and reaching the singularity is finite. It depends on the mass of the black hole. For a stellar mass black hole of 10 solar masses, the proper time between crossing the horizon and reaching the singularity is a tiny fraction of a second, much shorter than the time it would take to react to anything. Tidal forces would have already destroyed a human body well before the horizon crossing for such a small object. But setting that aside as a matter of scale, for a supermassive black hole of 1 billion solar masses, the proper time between crossing the horizon and reaching the singularity is on the order of hours to perhaps a day. Enough time to do science if the tidal forces are survivable, which, for a sufficiently massive black hole, they might be near the horizon. You would have time to observe the interior. Time to try to make measurements of what can only be seen from inside. To see physics that no observer outside has ever or could ever see. And then the singularity approaches. General relativity says it is a point of infinite density and infinite curvature. But almost no physicist believes that general relativity is telling the truth at that point. The infinite values are signals that the theory has reached its limits. The actual physics of the singularity requires a theory of quantum gravity, and we don't have one. Not a complete, tested, reliable one. String theory offers predictions. Loop quantum gravity offers different ones. Other approaches offer still others. What most of them share is the expectation that the singularity is not actually a singularity. That at the Planck scale, the extreme density does not go to infinity. Something else happens. The fabric of space-time itself undergoes some quantum transformation. Maybe a bounce. Maybe a transition to a different phase. Maybe something entirely without analogy in our current conceptual vocabulary. The interior of a black hole, past the event horizon, past the point of no return, is the only place in the known universe where physics would give us an unobstructed view of quantum gravity. If only we could reach it and come back. We cannot come back. The event horizon forbids it. Whatever is learned inside stays inside. The most extreme laboratory for fundamental physics is permanently inaccessible to any external observer. This is either deeply frustrating or deeply fitting, depending on how you think about it. The boundary that marks the limit of what we can physically reach from outside is also precisely the boundary that marks the limit of what our current theories can describe from inside. The event horizon is the edge of the known universe in a very precise sense. Not the edge of what exists. The edge of what can reach us, and the edge of what our theories reliably describe. There is one more aspect of the event horizon worth dwelling on. The way it changes over time from the outside. A black hole is not static. It grows when it swallows matter. The event horizon expands. Each time gas falls in from the accretion disk, each time a star passes too close and gets torn apart by tidal forces in a process called a tidal disruption event, the mass of the black hole increases. The Schwarzschild radius increases proportionally. The event horizon pushes outward, expanding to accommodate the new mass. There is a theorem in general relativity called the area theorem, proven by Stephen Hawking in 1971. It states that the total surface area of all event horizons in the universe cannot decrease over time. In any interaction or merger involving black holes, the combined area of the event horizons afterward must be at least as large as the combined area before. This theorem has a deep connection to thermodynamics. In thermodynamics, there is a law called the second law, which states that the total entropy of a closed system cannot decrease. The resemblance between the area theorem and the second law is not a coincidence. Black hole entropy, the Bekenstein-Hawking entropy, proportional to the event horizon area, makes the connection precise. The entropy of black holes, measured by their horizon area, behaves exactly like thermodynamic entropy. It can increase. It can stay the same. It cannot spontaneously decrease. This is one of the most beautiful unifications in physics. An abstract geometric object, the area of an invisible surface in space-time, obeys the same fundamental law as the entropy of a cup of coffee cooling on a table. The universe applies the same accounting rules to the largest and the smallest, to the event horizon of a supermassive black hole and to the atoms in a gas. When Hawking radiation was added to the picture, the situation became more subtle. Hawking radiation carries energy away from the black hole. The black hole loses mass. The event horizon shrinks. The area decreases. This seems to violate the area theorem. But the area theorem was derived from classical general relativity before quantum effects were included. When you account for the entropy of the Hawking radiation itself, adding it to the entropy of the black hole's horizon, the total entropy, horizon plus radiation, still increases. The second law is preserved. The accounting just has to be done more carefully when quantum effects are included. This generalized version is sometimes called the generalized second law of thermodynamics. It holds even when black holes are evaporating. The universe insists on it. By now, we have covered the event horizon from nearly every angle available to current physics. The geometry that creates it, the mass scales that produce it, what it does to time, to information, to the paths of particles, the rotating case and the ergosphere, the photon sphere that creates the black hole's shadow, the conflict with quantum mechanics over information, the firewall paradox, the holographic principle, Hawking radiation and thermodynamics, primordial black holes and neutron stars, the images captured by the Event Horizon Telescope, and yet the event horizon resists being fully understood. Every angle we approach it from reveals a new tension, a new question, a new place where the physics strains. This is not a sign that the science is weak. It is a sign that the event horizon is sitting at the precise location where the universe is telling us that our current theories are incomplete, that something beyond what we know is waiting to be discovered. The event horizon is not just an interesting feature of extreme astrophysics. It is a pointer, a landmark, a place in the universe where physics has left a note saying, "Here is where the current understanding ends. Here is where the next revolution will have to begin." Physicists have been working on that revolution for over a century. They are still working on it. The event horizons of the universe are waiting patiently. Think about what it means that these boundaries are real, not theoretical, not speculative. They exist, right now, surrounding every collapsed stellar remnant massive enough to have made the crossing, surrounding every supermassive concentration at the center of every large galaxy we can observe. Sagittarius A, at the center of our own Milky Way, is sitting 26,000 light-years from where you are. Its event horizon is a sphere about 14.8 million miles in diameter. At this moment, while you're reading this, while you breathe and think and go about whatever your day is, matter is spiraling into it through the accretion disk. Stars are orbiting it at thousands of miles per second. Space-time is curved severely in its vicinity. Time is passing more slowly there than here, and the boundary of its event horizon is sitting quietly in the dark, doing exactly what it always does, existing as the most absolute edge in the universe, not asking anything of the space around it, not announcing itself, just being the line past which the future has only one direction. Everything that has ever crossed that specific boundary has gone somewhere we cannot follow. A star that wandered too close 1,000,000 years ago. Gas from a molecular cloud that fell in 10,000 years ago. A stray particle that crossed the threshold a second ago. All of them moved through the same invisible surface. All of them continued on inside. None of them could send a message about what they found. The universe has arranged itself so that the most extreme place it contains is the one we are least able to study from the outside. The one place where the physics changes most dramatically is the one place from which no observer can return to tell us. And that boundary, that irreversible edge, has been imprinted on space-time itself in every corner of the observable cosmos. Tens of billions of galaxies, most of them with supermassive black holes at their centers. Each one surrounded by an event horizon, a geometric surface encoding the maximum entropy of its interior, a boundary that thermodynamics honors, that quantum mechanics struggles with, that general relativity describes but does not fully explain. A point in space where gravity stopped negotiating a long time ago. There is a phenomenon connected to the event horizon that is so extreme it barely seems like physics anymore. It is called a tidal disruption event. Stars in the central regions of galaxies don't just fall quietly into the black hole. The vast majority of them never come close. They orbit the supermassive black hole the same way stars orbit any other massive concentration of mass, maintaining stable orbits for billions of years. But occasionally, a star's orbit is perturbed. It might be nudged by the gravitational influence of another nearby star. It might be scattered by a close encounter. It might wander too close to the edge of a stable orbit. And when a star gets close enough to a supermassive black hole, something extraordinary and violent happens. Not because it crosses the event horizon, but because the tidal forces become strong enough to overcome the star's own gravity. Every star is held together by gravity. The gas and plasma that make up the star are attracted to each other, to the center of mass of the star itself. That self-gravity is what gives stars their spherical shape, what keeps them from simply dispersing into space. But when a star approaches a supermassive black hole closely enough, the black hole's gravity starts pulling on the near side of the star more strongly than on the far side. The difference in gravitational pull across the diameter of the star, which is what we call the tidal force, begins to stretch the star. At a certain critical distance, called the tidal disruption radius, this stretching exceeds the star's own self-gravity. The star can no longer hold itself together. It is pulled apart. torn into a long, curving stream of gas by the differential gravity of the black hole. About half of this gas stream gets flung outward on hyperbolic trajectories and escapes the black hole entirely. The other half falls inward, eventually spiraling around to join an accretion disk or fall directly into the black hole. As this material spirals inward, it releases an extraordinary amount of energy. The gas heats up dramatically. It radiates intensely across a wide range of wavelengths. For months to years after the disruption, the region around the black hole can be brightened to a luminosity approaching or exceeding that of an entire galaxy. A single shredded star can briefly outshine hundreds of billions of other stars. These events are called tidal disruption events, and astronomers have now observed dozens of them. They are dramatic. They are violent. They are visible from billions of light years away. And yet the event horizon itself plays almost no direct role in the drama. The tidal disruption happens outside the event horizon. The radiation from the infalling material is produced outside the event horizon. What crosses the horizon is the final remnant of gas that made it past the point of no return. The fireworks all happen in the last few moments before that line. The event horizon just sits there, patient and permanent, waiting at the end of the process, collecting everything that finally falls through and letting none of it back. Tidal disruption events have become an important tool for studying supermassive black holes that are otherwise quiescent. A black hole that is not currently actively feeding through a large accretion disk is extremely difficult to observe directly. It produces no strong radiation. It announces its presence only through the gravitational influence on nearby stars. But when a tidal disruption event lights up the region around a quiet black hole, suddenly we get a detailed look at the black hole's mass, its spin, and the properties of its immediate environment. A chance to study the vicinity of an event horizon that would otherwise remain dark and silent. The event horizon, in other words, has a way of making itself known through what happens just outside it, even when nothing is actively crossing. Consider the deepest question the event horizon raises about the nature of space itself. Outside the event horizon, the 3 dimensions of space and 1 dimension of time behave in familiar ways. You can move forward or backward in space. You can move left or right, up or down. You can orient yourself in any spatial direction and move there. Time, on the other hand, flows in one direction only, forward. You can move through space in any direction. But you cannot move backward in time. Time has a preferred direction in our part of the universe. It is not spatially symmetric. This asymmetry of time is one of the most fundamental puzzles in physics. The laws of physics at the microscopic level are almost entirely symmetric in time. Run a video of 2 billiard balls colliding in reverse, and it looks like a perfectly valid physical interaction. Run a video of a building collapsing in reverse, and it immediately looks wrong. Something about macroscopic reality breaks the time symmetry that the microscopic laws allow. This is connected to entropy, to the second law of thermodynamics, to the fact that the early universe had extremely low entropy, and the universe has been increasing its entropy ever since. The direction of time we experience is the direction in which entropy increases. This is a deep and not fully resolved issue in the foundations of physics. Now cross the event horizon. Inside the black hole, the time-like direction, the direction along which time flows, has been redirected. What was a spatial direction toward the singularity has become the future direction of time. You might think of it as the time dimension and one's spatial dimension having swapped roles. Outside the horizon, you are stuck moving forward in time, but can move freely in space. Inside the horizon, you are stuck moving toward the singularity, but can move freely in what used to be the time direction. The physics of this is encoded precisely in the Schwarzschild metric, the mathematical description of the space-time geometry. The component of the metric that describes time and the component that describes the radial direction switch signs when you cross the horizon. Positive becomes negative and vice versa. The time-like direction becomes space-like and vice versa. This is not a metaphor. It is a mathematical fact about the geometry. What you experience as the inexorable flow of time, the thing that makes you older, the thing that connects your memories to your present, to your future, has been redirected inside the horizon. It now points at the singularity. All the properties of time that you take for granted outside, the way it carries you forward, regardless of your choices, the way it defines what future means. Those properties now belong to the radial direction inside the black hole. The singularity is not a place you fall toward. It is a time you fall toward. It is, in the most literal physical sense, the future inside a black hole. There's a thought experiment that physicists use to probe the implications of this. Imagine you are floating far from a black hole, watching a friend fall in. Your friend is wearing a watch. As they fall toward the horizon, you watch their watch through your telescope. At first, the watch ticks normally. As they get closer to the horizon, the ticks appear to slow. Gravitational time dilation is at work. Closer still, the watch appears to slow more dramatically. The light reaching you from the watch is increasingly redshifted. The photons have to climb out of an increasingly deep gravitational well to reach you. They lose energy in the climb. Energy and frequency are linked for photons. Losing energy means decreasing frequency, which for light means shifting toward longer wavelengths, toward red, toward infrared, eventually toward radio waves. At the event horizon itself, the redshift is infinite. The photons emitted right at the horizon take an infinite amount of coordinate time to reach you. They effectively never arrive. Your friend's image at the horizon is redshifted to zero frequency, dimmed to zero brightness, frozen at the moment of crossing. You never see them cross. Your friend, of course, sees things very differently. From their perspective, they fall through the horizon in a finite, short amount of their own proper time. Their watch continues ticking normally. They feel nothing special at the crossing, and they would have a very interesting observation of their own. As they fall, light from the outside universe continues to reach them. Even inside the horizon, incoming light from outside can still reach the infalling observer. The event horizon is one way for outgoing light, not for incoming. Your friend, after crossing, would still see the universe outside. Light from distant stars would still reach their eyes. They could still observe galaxies, stars, the familiar universe. But they would notice that the view is distorted. The light from the outside universe would be concentrated into a smaller and smaller region of their visual field as they fell deeper. The entire outside universe would appear to be shrinking into a bright spot above them, blue-shifted, energetic, compressed. The sky below them, in the direction of the singularity, would be dark. As they approached the singularity, the light from the outside universe would be compressed into increasingly smaller angles and increasingly shorter wavelengths, more and more energetic, potentially lethal in terms of radiation dose, depending on the time they spent falling. And then the tidal forces would become dominant. For a stellar mass black hole, this moment comes quickly. For a supermassive one, there might be time to observe and measure before the tidal forces become significant. And then the singularity, and the silence of physics running out. The thermodynamics of black holes deserves more attention than it often gets. When Stephen Hawking and Jacob Bekenstein worked out the thermodynamic properties of black holes in the early 1970s, they weren't expecting to find what they found. Bekenstein had proposed, on theoretical grounds, that black holes must have entropy. He reasoned that if black holes had no entropy, you could violate the second law of thermodynamics simply by throwing high entropy material into a black hole. The entropy would disappear from the observable universe. The total entropy would decrease. The second law would be violated. That couldn't be right. So black holes must carry entropy. And the entropy must be proportional to the event horizon area. Hawking initially resisted this idea. He thought it led to an absurdity. If black holes had entropy, they would have to have a temperature. If they had a temperature, they would radiate like any other hot object. But black holes don't radiate. Nothing escapes from them. So they couldn't have a temperature. Bekenstein's idea seemed to lead to a contradiction. Then Hawking found his radiation, and the contradiction dissolved. Black holes do radiate. They have a temperature. The thermodynamics is consistent. All four laws of thermodynamics have analogues in black hole physics. The zeroth law of thermodynamics says that a system in equilibrium has uniform temperature throughout. The black hole analogue is that the surface gravity of a stationary black hole is constant across its event horizon. Every point on the horizon has the same gravitational pull. The first law says energy is conserved. The black hole analogue relates changes in mass, angular momentum, and charge to changes in the horizon area. When you add mass to a black hole, the energy balance works out consistently. The second law says total entropy cannot decrease. The black hole analogue is the area theorem. The total area of event horizons cannot decrease in any classical process. The third law says you cannot reach absolute zero temperature. The black hole analogue is that you cannot reduce the surface gravity of a black hole to zero in any finite process. The mathematical correspondence between these four laws and their black hole counterparts is exact, not approximate, not metaphorical. Exactly the same structure, the same relationships, expressed in the language of event horizon geometry. This is either a profound coincidence, or it's telling us something fundamental about the relationship between gravity, information, and thermodynamics. Most physicists believe it's the latter. That the thermodynamics of event horizons is not an analogy with thermodynamics. It is thermodynamics, applied to the geometry of space-time itself. The event horizon is not just a boundary in space. It is a thermodynamic object, a surface that carries entropy, radiates at a specific temperature, and obeys the same fundamental laws that govern the cooling of a cup of coffee. The universe appears to apply the same accounting principles at every scale. Perhaps one of the most startling things about the event horizon is how many different routes in physics lead to it. You can start from the mathematics of general relativity and find it as a feature of the Schwarzschild solution. You can start from thermodynamics and find it through the entropy-area relationship. You can start from quantum field theory and find it through Hawking radiation. You can start from information theory and find it through the information paradox. You can start from holography and find it through ADS, CFT. Every major branch of theoretical physics has its own path to the event horizon. And each path arrives at a slightly different picture, emphasizing different aspects, facing different paradoxes. The way different maps of the same territory can agree on the major features but emphasize different details. This convergence of multiple independent approaches on the same object is generally a sign in physics that the object is pointing at something real and fundamental, not just an artifact of one particular way of doing the calculation. The event horizon is where gravity, quantum mechanics, thermodynamics, information theory, and geometry all intersect. It is the crossroads of modern theoretical physics, the place where the threads of the deepest questions about the universe all meet. And it is sitting there in physical reality, not just in mathematical abstractions. Sagittarius A is real. Messier 87's black hole is real. The thousands of smaller black holes scattered through the Milky Way are real. The supermassive black holes at the centers of the hundreds of billions of galaxies in the observable universe are real. And every one of them is surrounded by an event horizon, a real, physical, geometrical boundary in space. A point where gravity became irreversible, and where the deepest questions in physics are waiting for us. The night sky, even seen with the naked eye, contains clues to what we've been discussing. The fuzzy band of the Milky Way, stretching across a dark sky, is the disk of our galaxy seen from inside. Toward the center of that band, in the direction of the constellation Sagittarius, is where the galactic center lies. It's hidden from direct optical view by enormous clouds of dust, billions of intervening stars, and gas spanning thousands of light years. You cannot see Sagittarius A with your eyes or with an ordinary telescope aimed at visible light. But it is there. Astronomers know this, not from speculation, but from direct observation. Using infrared telescopes that can penetrate the dust, astronomers have been tracking the stars in the central parsec of the galaxy for decades. These are called the stars. They orbit an invisible point at the galaxy's center. Their orbits are precise, measurable. The fastest of them, called S2, has an orbital period of about 16 years. At its closest approach to the galactic center, S2 passes within about 120 astronomical units of Sagittarius A, moving at about 3% of the speed of light. The star's orbit is so tightly curved, its speed so extreme, that the mass required to produce that orbit can be calculated precisely. About 4 million solar masses, all concentrated within a volume smaller than our solar system. Nothing else in physics produces a gravitational influence like this. The conclusion is unambiguous. Sagittarius A is a black hole, a supermassive one. Its event horizon sits 26,000 light-years from where you are reading this, and it has a radius of about 7.4 million miles. The astronomer Andrea Ghez at UCLA and the astronomer Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics spent decades tracking these stellar orbits around Sagittarius A. In 2020, they shared the Nobel Prize in Physics for providing the most compelling evidence that a supermassive black hole exists at the center of the Milky Way. They measured orbits. They watched stars swing around an invisible center at fractions of the speed of light. They saw general relativity playing out in real time, with the precession of the orbits matching Einstein's predictions precisely. The event horizon of Sagittarius A was never directly part of the measurement. You can't measure something that neither emits nor reflects anything, but its presence is written into every orbit those stars trace. The boundary of irreversibility imposes itself on the entire surrounding environment. Stars, going about their ancient orbits, hundreds of billions of miles from the horizon, carry its signature in the shape of their paths. The Event Horizon Telescope project that produced the first images of black holes has plans to extend its reach. The next generation of the Event Horizon Telescope is expected to add new stations, including space-based components, increasing both sensitivity and resolution. With improved instruments, the collaboration expects to produce higher resolution images of both Sagittarius A and the Messier 87 black hole, images that resolve features within the photon ring, that show how the accretion disk varies over time, that potentially allow measurement of the black hole's spin through the exact shape and brightness distribution of the ring. A black hole's spin creates an asymmetry in the shadow. The brightness of the ring on the approaching side is enhanced by Doppler boosting. The shape of the inner edge of the ring is affected by the spin. A precisely measured image, with enough resolution to see these fine details, would allow direct determination of both mass and spin, two of the three numbers that entirely characterize a black hole. The third is electric charge, which is expected to be essentially zero for astrophysical black holes, since any charge would quickly be neutralized by surrounding plasma. Knowing the spin of Sagittarius A and Messier 87's black hole with precision would constrain models of how they grew. A rapidly spinning black hole grew primarily by steady accretion from a consistent direction. A slowly spinning black hole may have grown through chaotic mergers from multiple directions, with the angular momenta partially cancelling. The spin is a fossil record of the black hole's history, encoded in the geometry of the event horizon. Readable, at least in principle, from images taken 54 million light-years away. Gravitational wave astronomy also has an expanding role to play. The LIGO, Virgo, and CAGRA detectors currently operating are most sensitive to stellar mass black hole mergers and neutron star mergers. They detect the gravitational waves produced as two compact objects spiral together and cross each other's event horizons. The merger of two black holes, the moment when two separate event horizons become one, produces a characteristic gravitational wave signal called a ringdown. As the newly merged black hole settles into its final configuration, it oscillates and radiates gravitational waves at specific frequencies determined by its mass and spin. This ringdown is essentially the event horizon ringing like a bell. The frequencies and damping times of the ringdown encode the black hole's final mass and spin. Measuring these precisely tests general relativity in its most extreme regime. So far, the ringdown measurements are consistent with general relativity's predictions. The event horizon rings, as Einstein said it should. Future gravitational wave detectors will be sensitive to much lower frequencies corresponding to much more massive systems. The space-based LISA detector, planned for launch in the 2030s, will detect gravitational waves from merging supermassive black holes in distant galaxies. when two galaxies merge, their central supermassive black holes eventually spiral together and merge as well. This process produces gravitational waves at frequencies far too low for ground-based detectors, but accessible to a space-based instrument. LISA will detect these mergers from billions of light-years away, observing event horizons colliding and combining across cosmic distances. And pulsar timing arrays, networks of millisecond pulsars spread across the galaxy, have recently reported evidence for a background of gravitational waves filling all of space. This background is thought to come from the combined gravitational wave emission of millions of supermassive black hole binary systems across the universe. Countless pairs of event horizons slowly spiraling toward their eventual merger, each one emitting a tiny contribution to the overall gravitational wave hum. The sum of all those contributions is now measurable. We are hearing, in a very indirect sense, the sound of event horizons across the observable universe. There is one final thing to consider. What the event horizon means, not just for physics, but for the structure of scientific knowledge itself. Science progresses through observation, prediction, and test. A theory makes a prediction. An experiment checks whether the prediction is right. If it is, we gain confidence in the theory. If it isn't, the theory must be modified or replaced. This method has produced extraordinary results. General relativity has survived every test ever applied to it. Quantum mechanics has survived every test ever applied to it. Both are extraordinarily well-confirmed theories. But the event horizon presents a challenge to this method. If you want to test what happens inside an event horizon, you have to go in. And if you go in, you can never return to report your results. The experiment is permanently isolated from the scientific community. An observer inside the horizon could, in principle, make observations and measurements. They could test whether the physics inside matches the predictions. They could investigate the approach to the singularity, see whether quantum effects modify the geometry, determine what actually happens at the endpoint. But none of that information can ever reach the outside universe. The scientific method, in its most fundamental form, requires that experiments produce results that can be communicated and checked by other scientists. The interior of a black hole is the one region of the universe where this requirement cannot be met. Not because the technology is insufficient, not because the experiments are too difficult, but because the geometry of space-time itself prevents any information from escaping. This is a genuine epistemic boundary, a limit not on what exists inside, but on what can ever be known from outside. The universe has a region where events happen, physics operates, and matter and energy evolve, and that region is permanently disconnected from the external scientific community. Some physicists find this deeply troubling. Others find it fascinating. The universe appears to contain places that are fundamentally and permanently private, where the laws of physics apply, but the results of those laws applying can never be verified from the outside. The event horizon is not just a one-way door for matter and light. It may be a one-way door for knowledge, a boundary not just of gravity, but of epistemology, of what it is even possible to know. And this, perhaps more than the extreme gravity or the distorted space-time or the information paradox, is what makes the event horizon the most singular object in the universe. It is not just the most extreme physical boundary we know of. It is the limit of what the universe will let us understand. The point where gravity becomes irreversible is also the point where science, in its usual form runs out. And beyond that point, the universe keeps its own counsel. There's a concept in black hole physics that doesn't get enough attention in popular explanations. It's called the interior geometry, and it's far stranger than most descriptions of black holes convey. When you think about the geometry inside a black hole, the natural mental image is a deep well. A gravitational pit with the singularity at the bottom and the event horizon as a rim around the top. You fall in, you go deeper, eventually you reach the bottom. This picture is wrong in a fundamental way. It treats the interior of a black hole as though it were a region of space, a volume you fall through, with the singularity as a location inside that volume. But we've already established that inside the event horizon, the singularity is not a location. It's a time. The full implications of this are worth drawing out carefully. Outside the horizon, the future is a direction in time. You move through space freely in all directions, but you cannot move backward in time. The boundary between accessible regions of space-time and inaccessible ones is drawn by time. You cannot reach past events. Inside the horizon, the singularity is in the future, in the same sense that tomorrow is in your future right now. It is not a place you can avoid by moving in a different spatial direction. It is a time that is coming, regardless of your spatial position. You could move left, right, up, down, in any spatial direction inside the black hole. You could accelerate or decelerate. You could orbit, tumble, drift. None of it would delay your encounter with the singularity, any more than moving around inside a room delays the arrival of midnight. The singularity will arrive. It is your future, not your spatial destination, your temporal destination. Now here is where the geometry gets stranger still. When physicists talk about the interior geometry of a Schwarzschild black hole, they often use what are called Kruskal-Sekeres coordinates. These are a mathematical coordinate system that covers the entire spacetime without the coordinate singularities that appear in the original Schwarzschild coordinates. In Kruskal-Sekeres coordinates, you can see the full causal structure of the black hole spacetime, and what you see has a surprise. There are actually 4 distinct regions. The exterior region we're familiar with, the interior of the black hole, a second exterior region that is causally disconnected from the first, a mirror image of our universe, in a sense, and a white hole region, which is the time reverse of the black hole. The white hole is a region from which things can only escape, never enter, the exact time reverse of a black hole. These additional regions are part of the maximal extension of the Schwarzschild geometry. They appear in the mathematics when you extend the solution beyond the original coordinates. The 2 exterior regions are connected by what is called an Einstein-Rosen bridge, a narrow throat of spacetime connecting the 2 otherwise separate regions. This is a wormhole. The same wormhole solution that Einstein and Rosen described in 1935 when they were examining the structure of the Schwarzschild solution. But this wormhole is not traversable. It pinches off too quickly. Even a photon cannot cross from one exterior region to the other. The bridge forms and collapses faster than anything can travel through it. In real black holes formed from stellar collapse, only part of this structure exists. The second exterior region and the white hole region are not present. They are features of the idealized eternal Schwarzschild black hole, one that has existed and will exist for infinite time. Real black holes formed at a specific moment in cosmic history when a star collapsed. Their interior geometry is more limited than the eternal case. But the white hole and the second exterior region hint at the richness of what the mathematics is telling us about the structure of space-time around extreme mass concentrations. There is also the question of what surrounds black holes at the boundary of what we can directly observe. The accretion disk has been mentioned multiple times, but its structure is worth more attention. The accretion disk is not simply a flat ring of gas uniformly falling inward. It is a complex, turbulent, magnetized system with structure at many scales. The gas in an accretion disk is hot, extremely hot. Near the inner edge, closest to the event horizon, temperatures can reach billions of degrees. Gas this hot is not simply gas in the usual sense. It is a plasma, a gas of free electrons and ions, fully ionized, in which magnetic fields are embedded and play a crucial role. The dominant source of turbulence in accretion disks is a process called the magnetorotational instability. In any rotating disk of conducting fluid threaded by magnetic field lines, small perturbations grow rapidly. The magnetic field provides a coupling between neighboring rings of gas. Inner rings orbit faster than outer rings. The magnetic coupling between them transfers angular momentum outward. Gas in the inner ring is slowed, loses angular momentum, and falls inward. Gas in the outer ring gains angular momentum and moves outward. This sounds like it would prevent accretion. Inner gas falls in, outer gas moves out. Net result is nothing gets to the black hole. But the instability doesn't just move gas radially. It also heats the disk, drives turbulence, amplifies the magnetic field, and drives a continuous inward flow of mass. The magnetorotational instability is what allows accretion disks to actually feed black holes, rather than just sitting there rotating. Without it, the gas would stay in stable orbits forever, and the black hole would receive nothing. The instability is the engine that drives mass through the event horizon. Beyond the disk itself, many active black holes produce jets, narrow beams of energetic particles and electromagnetic radiation shooting out from the poles of the black hole, perpendicular to the disk. These jets can extend for hundreds of thousands or even millions of light years. Messier 87's jet is about 5,000 light years long. The jets of some quasars extend for millions of light years, punching through the surrounding galaxy and into intergalactic space. The jets are launched by a combination of the rotating space-time near the event horizon and the magnetic fields threading the accretion disk. The exact mechanism is called the Blandford-Znajek process, after two physicists who described it in 1977. The rotating space-time near the Kerr black hole winds up the magnetic field lines threading the disk. The wound-up magnetic field accelerates particles along the rotation axis. These accelerated particles form the jet. The energy comes from the black hole's rotation. The ergosphere, the region of dragged space-time outside the event horizon, is where the energy is extracted. The jets carry away the rotational energy of the black hole, slowly spinning it down over cosmic timescales. Black holes that power the most energetic jets are the most rapidly rotating. The event horizon's spin is directly expressed in the energy of the beam of particles shooting into intergalactic space. These jets have real effects on the surrounding environment. When a jet plows into the gas of a galaxy cluster, it heats that gas. It prevents the gas from cooling and falling inward to form new stars. The black hole at the center of a galaxy by launching jets powered by the rotational energy of its event horizon, can regulate star formation across the entire galaxy. The most massive elliptical galaxies in the universe owe their shapes and stellar populations, in part, to the fact that their central black holes are firing jets that prevent gas from cooling and forming stars. The event horizon of a supermassive black hole reaches across galactic scales. Not directly, not through any force that crosses the horizon, but through the jets it powers, through the energy it extracts from the ergosphere. The event horizon is the engine. The jets are how its influence propagates outward, changing the properties of the surrounding galaxy and even the galaxy cluster in which that galaxy sits. An invisible geometric surface, a few billion miles across, shaping the environment of regions spanning millions of light years. The scale of influence from such a compact boundary is almost incomprehensible. One of the questions that gets asked often when people start thinking seriously about black holes is whether a black hole could eventually consume everything. Whether the universe would end with all matter having fallen through event horizons. The answer depends on timescales so extreme that they make any ordinary duration irrelevant by comparison. In the current universe, black holes grow by accreting gas, dust, and stars from their surroundings. This process is efficient when the black hole has a large supply of material nearby. In an active galaxy with a large accretion disk, the black hole can swallow mass at rates of several solar masses per year. But eventually, the material runs out. The gas is consumed. The nearby stars are too distant to be easily pulled in. The black hole becomes quiet. Sagittarius A is in roughly this state right now. It is not actively consuming large amounts of material. It is sitting there, largely quiet, growing very slowly as the occasional star passes too close or gas drifts into its vicinity. Over very long timescales, the universe itself changes. Stars burn out. The last stars will form and then burn out over timescales of perhaps 100 trillion years. After that, the universe will consist mainly of stellar remnants, white dwarfs, neutron stars, black holes, and cold, dark matter. Black holes in this dead universe will grow very slowly, capturing the occasional passing remnant through gravitational interactions. The event horizons will expand, but very slowly. Much, much later, quantum effects that are negligible today become relevant. In a cold, dark, nearly empty universe, the background temperature approaches absolute zero. In that environment, even the faint Hawking radiation from black holes is significant. Black holes will eventually evaporate. The most massive ones will take the longest, but given enough time, all black holes will lose mass through Hawking radiation faster than they gain mass from their environment. They will shrink. Their event horizons will contract. They will eventually, after timescales that make the age of the universe look like the blink of an eye, disappear entirely. The event horizon, having been the most permanent boundary in the universe, will cease to exist. The points of no return will, one by one, be reversed by quantum mechanics. The universe will move from a state in which event horizons exist and grow and trap matter, to a state in which they shrink and evaporate and leave nothing behind. What that means for the information they captured, what happens to the quantum states of everything that fell through, is exactly the question the information paradox asks. The resolution of that paradox, whatever it turns out to be, will describe the final accounting that the universe does when the last event horizon fades. If you found tonight valuable, a like or subscribe helps more than you might think. It lets this channel reach more people who genuinely want to understand how the universe works, not just what it looks like, but what it actually is and why. The next time you look toward the center of our galaxy, toward the dense band of the Milky Way stretching across a dark sky, remember what sits there. 26,000 light-years away, behind the dust and gas and billions of intervening stars. A sphere of permanent irreversibility, sitting quietly in the center of our galaxy. A place where space-time made a decision about what forward means. And everything inside it is moving toward an ending. The rest of the universe will never be allowed to see. Good night.